So let's take a look at the longest common subsequence problem that we started off in the last lecture. And as I said, this is it has a lot of applications in genome sciences. And for those of you who have that interest, you might find it interesting to explore this a little bit more. I'm always fascinated by DNAs and genome sequences and so on. So we saw the issue of how do you compare different organisms, different species, and there could be different ways of doing it. But the longest common subsequence is one way of doing it. And in fact, I was looking up and there were a number of papers still being published which actually try to find better ways of trying to solve the LCS problem when it comes to real-world genome issues. So hopefully you remember this from the last lecture. We defined what subsequences are, okay? And there are 2 to the power m subsequences for a string of length m. And then we said, we gave you some examples of how it's not that easy to be able to figure out the subsequences, because you could start, let's say, from 1x to y, and you could go over each one of these letters and see if there's a match on the other string. But then you could actually improve the match by skipping some of the characters, okay, as you saw in this particular example. And these were some other examples. And then we saw that if you did a brute force technique, then it would be a really expensive solution, order of n to the times 2 to the power m, or m to the power 2 to the power n, depending on which is smaller, m or n. Okay. And then we stopped at this slide in the last lecture where we started by defining a prefix. Okay. So the concept of a prefix is fairly simple. It simply takes, if you're talking about the ith prefix of any string, then you simply take the first I characters. Okay, so x sub I is simply x1 through x sub I. Okay, so now notice that we're differentiating between the uppercase x and the lowercase x's, and similarly the uppercase y and the lowercase y. So just keep track of that. Right, so those were the prefixes, and now we get to actually doing some of the tricky part. So we need to first of all prove the optimal the substructure property. Okay, so well, before proving it, we need to be able to identify whether an optimal substructure exists in the LCS problem. Okay, so here is the starting point where we say you have a string x and a string y comprises of m characters and n characters, and we'll start by saying, as I've repeatedly said in the past, is that when you want to show an optimal substructure, you start off by making an assumption. Okay, and the assumption is that you have a solution, and that is optimal. Okay, so we're going to make the same assumption. We're going to say that Z is a longest common subsequence of x and y. Okay, so we've already somehow found it, and it consists of k characters. Okay, so Z is defined to be the LCS of x and y. Right, now we're going to have 3 cases, and as we go through those 3 cases, we'll take a look at their proof, and also be able to determine a recursive solution to the problem. So let's start by the first case. And the first case says that what if x sub m is equal to y sub n? Okay, so x sub m corresponds to the last character of the first string x, y sub n is the last character of the second string. Okay, so x sub m happens to be equal to y sub n. And so my question to you is, in that case, if Z is the LCS of both X and Y, then what can you say about Z? Or in particular, Z sub K. Okay, so Z sub K, because it has a length of K, so Z sub K, the small letter Z sub K, is the last character of the string Z. So any thoughts? What can you say about Z sub k if X sub M is equal to Y sub N? And think about it in the sense of you're trying to show that perhaps it has an optimal substructure. We're not so sure. We already know that since it's on the topic of dynamic programming. So we know that there is going to be an optimal substructure coming up somewhere. Okay, but we just have to see how is the optimal substructure here different from perhaps the rod cutting example, or in some of the graph problems. Each one of these has a slightly different flavor. Okay. So what can you say about G sub k? So Z is an LCS, okay, of both of these. And the last characters of both of these happen to be the same. Yes. Would be equal to A in this case, right? Do people see that? Can I get your name? Thomas? So can you explain your reasoning, Thomas? Yeah. Yeah. So if they're both the same and Z is the longest common subsequence, and you already know that the last characters of these two strings is the same, then naturally the last character of your LCS will be equal to the last character of these two common strings. Does everybody see that? Okay, so hopefully that's clear. So that was the first thing. So now we're saying that Z sub k is equal to X sub M and Y sub N. Okay, so here's XM, here is YN. Okay, and here is Z sub k. So these three are going to be the same. Now, we're trying to show that it has an optimal substructure, right? So now, how should we proceed after that? Think about optimal substructure. So now, if you're thinking about minimum spanning tree or shortest path distance, then we sort of broke it up into two parts, and we said, well, if this whole thing is optimal, then the two parts are also optimal. Okay, the subparts are also optimal. So now, using that thought process, can you think about an optimal substructure to this particular problem? What can you say? So we've tried to see if a sub part of this problem is also optimal. Okay, so having shown the last characters are the same, can you break it down into a smaller problem and show that it is also going to be optimal? Yeah. So the first characters of each one of them. So you could start by looking at, let's say, the first characters. Let's say that would be Y sub 1, sorry, X1, and this would be Y1, and this would be Z1, right? So you're saying that we looked at the last character. Now let's go on the other end and look at the first characters and try to prove something similar, okay? And thereby maybe making it smaller, okay? So we're trying to make a recursive solution, and that's a good way to think about it, is to, can we attack both ends of the problem, all right? Can we make headway on this thought? Can I get your name again? Sorry. Isaac. So Isaac's thought about going in the direction starting from the beginning, can we make progress on that front? That's a novel thought, by the way. So let's think about that. Could we say something about that? could we say that if x1 is equal to, let's say put a double equals to y1, then can we say that z1 is going to be equal to x1 is going to be equal to y1? Is that going to be true? Yeah. Can we make a statement like that? Would you agree, Isaac? Okay. Interesting thought. So perhaps we could have, instead of looking at it at the last character, we could have worked from the front end. Okay, so we could have approached the problem from either one of those two directions. Okay, but the way the proof goes, at least as far as the book is concerned, we're going to restrict ourselves to one end. Okay, and if you're working from the right side, let's continue with that thought process. And because if you could either work from the right or from the left, but if you're working simultaneously from both ends, the proof doesn't, the problem doesn't become that much simpler. Okay, so let's keep this thought on the side and see that perhaps Isaac's suggestion can actually come up with a completely alternate proof, which is just a flip side of the current proof that we're going to go through. Okay, so give that thought a rest. Let's think about another way of proceeding. Is there another way to proceed to make the problem smaller? See, when Isaac, you're making the problem smaller from the left end, you're not building up on what you've already said. Okay, you suggesting a different strategy, which is fine. But what we need to do is build up on what we've just said. Okay, so continue with the thought on the right side. Yes. Yeah, very good. So let's say if you drop the last character, what would this be called, this entire string? There is a smaller terminology for that. That's the prefix. Yeah. So so that would be simply x of m-1, right? That's why we introduced the concept of a prefix. And we could take the first n-1 characters from y, and that would be called capital Y n-1. Is that right? Okay. And we could take the first k-1 characters from z, and from our terminology of a prefix, that would be capital Z k-1. Okay. So now we've got these three new strings. And what can we say about their relationship? Think about optimal substructure. Could we say something about the optimal substructure? Yes, continue. Yeah, perfect. Your name again, sorry. Sorry? Kenneth? Okay. So Kenneth's suggestion is head on. Okay, that's exactly right. So basically we've said, let's look at zk-1, okay, which I've shown here in blue, okay, right? And we have xm-1, which is the stuff over here, and yn-1, which is the first. We've just removed the last characters from each one of these. And basically what we're saying is that zk-1 is an LCS of xm-1 and yn-1. Now, does that make sense? And from the example that I have, you can see that, yes, that sort of does make sense, because we've said that all three of these characters are the same, right? So we've removed all of them. And now what we're saying is that BCB is the longest common subsequence of what is remaining in X and what is remaining in Y. Okay. So we can hopefully see that, but how would we prove it? And whenever you see, you've seen this frequently enough, whenever you have proofs like this, your first choice of proof strategy would be what? The by contradiction. And you start off by, before contradiction, you start off by doing what? Yeah, and that example would be based on, remember, there's a 3-word phrase for that. We like to do that a lot when we're working on word editors. Yes, cut and paste. Yeah. So cut and paste simply says, well, let's see if we can cut out some portion, replace it with a contradictory proposal, okay, and see if we can come up with the contradiction. So pretty much what you're saying, but there's a term for that, and cut and paste. So let's see. So how would we do a cut and paste proof over here? Any thoughts on that? How would we do a cut and paste? So you need to come up with a contradictory proposal, hypothesis, and then say, well, if that was true, then the original assumption would be, it would be contrary to the original assumption. So how can we do a cut and paste proof here? So what we could do, so basically what we're saying is that zk minus 1 is optimal, right? So it is the longest common subsequence. So what would be the first thing to prove that, to take an alternate hypothesis? Would be to say what? Well, think about the minimum spanning tree, right? Or the shortest path. We said, well, here is a path, and we're saying that the subpaths are also optimal. And then we said, well, assume that a subpath is not optimal, right? So how would that translate over here? Yes, Jane? Yeah, so we could use a prime notation for that. So we could say, let's assume that there is a z prime k minus 1, which is longer than zk minus 1. Okay, so this is, let's assume that this is not an LCS. Is not the longest common subsequence. There is another subsequence which is longer. Okay, so that's a good starting point. So after we assume that, what are we going to do? So remember again the MST, we assume that there is a longer path, and then we're going to cut and paste, right? So where do we paste that in? Where are we going to paste that in? Where are we going to, well, where are we going to, what are we going to cut out and what are we going to paste? Okay, so now think about z and zk minus 1, right? Think about z and zk minus 1. So here's z and zk minus 1 is smaller subsequence. Okay, we said that z is the longest common subsequence. It comprises of zk minus 1. We're saying zk minus 1 is not the longest, and there's some other subsequence which is longer, z prime k minus 1. So what are we going to do? Yes. Yeah. So we've added it back. So you have zk, or actually z, it becomes z. And here is one structure. Here is another structure, which is, you can call that z prime, okay? And z prime is basically z in which you've taken zk minus 1 out, okay? And you've replaced it with a longer subsequence, okay? And now what do we do? Yes. Yeah. Yeah, perfect. So everybody followed Thomas's thought process. Basically, what he just said is that you have the original z. It comprises of zk minus 1 and zk. And we're saying, well, this is supposed to be an optimal solution to the smaller problem. Let's assume that it is not. And we come up with zk minus 1 prime, okay, which is longer. And so we cut this out, replace that in, and we call that z prime, just like we did in the, the MST problems and other problems, okay? And so if this is longer than the original zk minus 1, then z prime will eventually come out to be longer than z. That again is a contradiction. Okay, so that's pretty much the standard proof in, I would say, I guess, all or the vast majority of dynamic programming proofs is that you do a cut and paste, and then you show that there's a contradiction. Okay, so this is what we've just done, and just to show it to you in a slightly more formal way, is that you've taken the original z, and you replaced zk minus 1 with z prime k minus 1, which is assumed to be longer. So I've shown it to be longer than this over here, okay? And so z prime is now simply a concatenation of z prime k minus 1 and a, okay? That is already there. And so that will come out to be showing that z prime is now longer. Okay, so, and z prime now becomes longer than the original z, which is again a contradiction. Okay. So if you've understood that part, the second and third parts are fairly similar. And I'm not going to go into as much detail, but hopefully your intuition will help you over there. So the second part is saying that now we're going to assume that these two are not equal. Okay, earlier we had assumed that xm is equal to yn. Right? Now we're saying that these two are not equal. Okay. And in addition, we're saying that z sub k is not equal to x. Okay, so z sub k is not equal to x sub m. So the last character of z is not equal to the last character of x. We're not saying anything about z sub k and y. Okay, that's to be noted. We're not making any statement over there. We're simply saying that these two characters are not matching in at least the second case. Okay, it's the second case. So if these two are not matching, then z is an LCS of the shortened version of x and the original version of y. Okay, so we've taken the shortened version of x because these two are not matching. So essentially we can drop that last character. All right, so we're going to drop this out. And we're going to say, well, here is a shortened version of x, which is xm minus 1. All right. And we keep the original version of y because we haven't said anything about that. Besides the fact that these two are not the same. Okay. And so z, the original z, without shortening it, is an LCS of the shortened version of x and y. Okay. Now you might say, well, is this really showing something about the optimal substructure? So not exactly. You can see that this thing was a lot more useful in being able to prove optimal substructure. But this is useful for recursion. Okay. And as we, whenever you have an optimal substructure, remember that leads us to a recursive solution. Okay. So we're trying to build up a solution for recursion. We're looking at different cases and we're saying, well, in recursion, you need to be able to work with a smaller problem. So how can we make it smaller? So we didn't have this property, but what we can say is that if these two characters are not matching, then we can reduce the size of x and keep the original y, and z, the original z will still be an LCS of the reduced version of x and the original y. Okay, so we made the problem a little smaller, and hopefully that can help us in finding a recursive solution. The third part is again exactly similar to number 2, except it's the reverse. And all it's saying is, again, we're making the assumption that these two are not equal, which was only for the first case. In the second two cases, xm and yn are not equal. And now we're saying that instead of saying zk is not equal to xm, we're saying that zk is not equal to yn, just the, the mirror image of that, or exact opposite. So z sub k is not equal to yn. And so then in this case, in the earlier case, z was an LCS of xm minus 1 and y. In this, we're saying that z is an LCS of x and a shorter version of y. Okay, so we've removed this because these two are not equal. So we can drop the last character of y. And then we can say, well, this and the shortened version, these two are that the original z is going to be an LCS of these two. Okay. So based on this, we can now come up with a recursive solution, and it's simply based on the previous 3 cases. And here is a sort of a summary of the 3 cases, and that's just without the examples. And so let's take a look at the recursive solution. So we're going to define Cij to be the length of the LCS, of an LCS, because there can be multiple LCSs. Yes. Yes, so you could have a 4th case as well, but that doesn't help us, but you could have that 4th case as well, okay? And you could make a statement about that, but that doesn't, it's not relevant to the recursive solution. So that's why it's not really discussed, but good question. So let's take a look at the recursive solution. So let's say we define Cij to be the length of an LCS of the sequences xi and yj. Okay, so now we're talking about the prefixes. All right, so these are not the original ones. These are the prefixes, and we're saying that we're taking a smaller prefix, which is all characters starting from the left up till I or j. For x, it's I, and for y, it's j. And we're comparing the initial portions from the left. Okay. And we're saying that Cij is the length of the longest common subsequence. So what happens if I is equal to 0 or j is equal to 0? Well, clearly that implies that one of those strings is a null string. So clearly the longest common subsequence is going to be 0. Okay, so that holds. The The middle one, the middle situation is the first case, okay, when x sub I is equal to y sub j. Okay, the only difference that we're saying is that we're not going with the last character, we're going with a certain portion, a certain prefix of the entire strings. Okay, so we're working with a certain prefix xi and yj. And we're saying that the last characters of those two prefixes are the same. And if that is the case, then we know that we have this particular situation where these two are equal. Okay, and so zk minus 1 is an LCS of the shortened versions of both x and y. So essentially, we're saying that we can add 1 to the longest common subsequence of both of them reduced by 1. Okay, which basically means that this is xi minus 1, and this here is yj minus 1. Okay, so if you can find the longest common subsequence of xi minus 1 and yj minus 1, and you add 1 to that, you should be able to get the LCS, the length of the LCS for Cij. Okay. And the last case is basically combines these two situations. Okay, cases 3 and 2. And basically it says that, well, if these two are not equal, all right, and you have one of those other two situations, then basically you need to find the maximum of the two. Okay, so either you'll find the maximum of yj minus 1 and the original x, or you reduce x by 1 and keep the original yj. Okay, and this comes in directly from the second two cases, the second and third case. So, so that's a recursive solution, and we can build up on that. So remember, every time we start off with dynamic programming problems, we start by showing us an optimal substructure. Once you have an optimal substructure, you can divide that up, that you can write an algorithm for a recursive solution, okay? And we proceed after that, okay? And then here we can actually show you a recursive tree. So for example, if you're trying to solve for the longest common subsequence of x4 and y3, then essentially what we're saying is that the worst case situation is that you need to be able to divide up that problem in this particular, the last part, and you look at the LCS lengths for either this being reduced, okay, which is 3, 3, x being reduced, or y being reduced, okay, which is x is being retained in length and y is being reduced. So 3 becomes 2, 4 is retained. In this case, 4 is reduced to 3, and the length of y is retained. Okay, so for 3 is basically, to be able to compute for 3, you may have to compute the LCS of 3, 3 and 4, 2, okay, because you need to find the maximum. And similarly, if you want to compute the LCS for 3, 3, you'll again have to do a recursion in which you reduce the size of x, keep y the same size, or you reduce the size of y, and you keep x the same size. Okay. So we can now visualize the recursive solution in terms of a recursive tree, right? So does it look good? Or do we see a problem? So is there a problem? Yes. Yes. So there is a lot of redundancy, there is a lot of overlapping subproblems, okay, which is great, because that's what we need to have a dynamic programming solution. So where can we see the repeats? You can see them all over the place. So you can see that to be able to solve for 2, you need to look at 3, 2, reducing x by 1. And to be able to solve for 3, 3, you need to be able to, one of the solutions is by reducing y by 1, okay? And both of them happen to become the same problem. C of 3, 2, C of 3, 2. Similarly, you see that there is a whole bunch of, even for a small case like this, you can see that there's a whole bunch of overlapping subproblems. So now what would be the solution? So you can see we're going through a series of steps, right? Optimal substructure, find a recursive solution, show that the recursive solution has overlapping substructures. And then what do? What's perhaps the last stage? Because this is not just, it hasn't been shown, it hasn't been converted into a dynamic programming solution, right? So now we need to convert it into a dynamic programming solution. And to convert it into a DP solution, what do you need to do? Yes, memoization, right? So in memoization, basically all you're saying is that we're going to keep track of the past results, okay? And so naturally, we're going to say, well, somehow we need to keep track of this two-dimensional structure, which is why I said that the rod cutting was sort of a one-dimensional problem, and the LCS is now a two-dimensional problem, because now you have to keep track of a two-dimensional structure, okay? So whenever you have something like this, people come up with interesting ways of representing that. And we're going to see an interesting way of finding the solution. And here is the solution. So we're going to have the table C, okay? And in addition, as you might have remembered, even the graph problems, we had an additional table, which was sort of keeping track of the parents, okay? The previous directions, where we're coming from, so that you can actually print out the result. So we're going to have two tables. The first one, which is C, is going to be the LCS length, which we defined over here. Okay, so Cij is going to be the length of an LCS of the sequences Xi and Yj. And the B table is going to help us keep track of the solution. Okay, and we'll see that in a few minutes. So here's an example, and we're going to start by assuming that X is given by A, B, C, B, D, A, B. All right, and this comes in from the book. So if you want to go over the solution and you want to look at the book, the fourth edition is, the solution is based on the fourth edition. And here is Y, and this is Y of 6, might say, and this is X of 7, which is the original length. And now the solution is going to proceed as follows. And remember, we generally use a bottom-up approach. Okay, we start by, remember in the rod cutting sequence, we started with 0 and we built up the solution to find the optimal revenues. So again, we're going to start from the bottom, and the bottom in this case is going to be starting with the indices I and J, starting from 0 going upwards. Okay, and you could do it in two different ways, but the solution in the book does it in row major order. Okay, so row major simply means that we're going to go row wise. Okay, so we're going to go horizontal and then come back this way, as opposed to going vertically on the rows. Okay, so we're not going to do this, but you could do that as well. There's nothing special about the x-axis versus the y-axis. So initially, we're going to start off doing some initialization. And the initialization essentially says that we're going to make the cases of, for I is equal to 1 to m. So we're going with I is equal to 1 to m. We're going to, for the value of j being 0, we're going to set these to be 0. Why do you think that's the case? And similarly, we're going to go from j is equal to 0, j is equal to 0 till n, and we're going to set the first row to be 0. So the first column and the first row are set to be 0. So does that make sense? Why do you think we're doing that? So if you look at, for example, Each one of these corresponds to the C table. Okay, so this particular, for example, entry corresponds to C 0, 6, right? So we're saying that the longest subsequence, the longest common subsequence for two strings, one of which is of size 0 and the other one is of size 6, the longest LCS is 0. Why is that? Yes. Yeah. Yeah. So if either one of the strings is a null string, then obviously you can't have any. The longest LCS is going to be 0. So that's and that also helps us. These are sort of sentinels. They help us in actually implement the algorithm as well. Okay. So after that, we're going to go forward and we'll start with I is equal to 1. So we're going to start with I is equal to 1 to N to M. All right. And then we go from J is equal to 1 to N. So we go from J is equal to 1 all the way up till N. All right. So essentially we're doing it in the row major order. And we're going to say the same things we said earlier. Okay, so we're going to have the three cases. If X sub I is equal to Y sub J, in other words, and now I need your help to be able to solve this. What are we saying when we say X sub I is equal to Y sub J? Which two characters are the same? So we're saying that X sub I is equal to Y sub J. Is A equal to B? Clearly no. So we're going to do the first part of the loop. We're not going to do the first part of the loop. We're going to jump to the next part. Okay. And then we're saying that if Ci minus 1, comma J, all right, Ci minus 1, comma J is this value here, okay, is greater than or equal to Ci, comma J minus 1. So is this chap over here bigger than this value over here, okay, or greater than or equal to? So is 0 greater than or equal to 0? Yes. So in that case, we're going to follow this this case, and we're going to say, well, Cij, so we're going to set the value over here, is going to be equal to Ci minus 1 J. Okay, so if this is greater than or equal to this, okay, so we're trying to fill out the value over here. If the one above is greater than or equal to the one on the left, then we're simply going to copy the value from the top. Okay, so we're going to set Cij to be equal to, and I'm showing you here this arrow, which is now basically going to be the B matrix. So we've sort of superimposed the C and the B matrices into a single matrix, and there are two values. There's going to be an integer, and then there's going to be an integer to correspond with the longest LCS, and there's going to be an arrow, which is sort of indicating where we're coming from. Okay, so the backtrack or the parent. So we've got this arrow over here. Let me sort of redraw this a little cleaner. So the arrow is now basically going upwards. Okay, and this arrow is going to be placed in this particular box. Let's do the next one. And now can somebody do the next one as well? Somebody wants to volunteer? So we're going to increment J. Now J is equal to 2. And I is still 1. Yes, Thomas? Yeah. Okay, perfect. So everybody got that? Okay. And similarly, if you keep on going, A and C are also not equal. So we're going to do the same thing over here. Okay. And finally, we come to an interesting case where they are equal. So now the A over here is equal to the letter A over here. Okay, so this is now going to fall into the first case. And now we're saying that x sub I is equal to y sub j. And so what are we going to do? Well, Cij. So we're going to set this value to be Ci minus 1, j minus 1. Okay, so it's going to simply say, well, this is going to be equal to the previous value. Okay, remember the recursive solution, plus 1. All right, so this comes out directly from the earlier case. So this is this particular situation where we're simply taking the LCS of the two smaller versions of x and y, and we're saying whatever was the solution over there, we're going to increment that by 1 because now we found the last character of both of them to be equal. Okay, so now this is going to be equal to 1 plus the diagonal value. Okay, so now I'm going to place a diagonal, which is going to correspond to the B matrix. And now we're going to add a 1 to 0, and that becomes a 1. Okay. So can somebody do the next one? Now we've incremented j to be 5, I is still 1, and we're saying we're comparing A and B, and A and B are not equal. So can somebody do that? Yes, Kyle. So we're going through the second case or the third case? In this case? Well, in this case, you're basically saying you're comparing the top to the left, and if this is greater than or equal to 1. So is 0 greater than or equal to 1? That'll be the third case, right? So it'll be the third case, and then you're going to put a left arrow. Okay, so you're going to copy 1 from the left side, and we're going to put a left arrow here. Okay, simply because 1 was greater than 0. The last case, so now A and A are equal. So now somebody do this one. This is the case where the two A's are now equal. So which of these three cases do we follow? And what will be the value over here? And where will the arrow point towards? Yes, Jay. Yeah. Yeah. So you'll have a diagonal arrow, and what will be the value? 1. So it'll be 0 plus 1. So that's how it should be. Okay. So so if you analyze this situation, and let me get rid of some of this extra stuff here. So if you analyze the situation, basically what we've said is that if you just compare A with all of these, then you've got a match over here, and you've got a match over here. And you could just stop over here and say now you've got an LCS, and the LCS is A. Or you could use this particular match, and this is also finding an LCS, but it's a different A. Okay, both of them are valid solutions, but you've got two acceptable solutions. They look alike, but they've been drawn from different portions of the Y string. Okay. So let's spend another few minutes just doing the second row, because the second row may offer us some different challenges. Probably not, but well, let me just, for the sake of time, I'm going to show you the solution. Let's take a look at this. So this is what we've done. I think this is what we had. Yeah. So we've done up till here. If you look at the second row, okay, so you're going to see, well, there's a match over here, B and B. So we're going to take the diagonal arrow, and we're going to add a 1. We're going to make point a diagonal arrow here. In this case, there is no match between B and D. So because 1 is greater than 0, the arrow is going to point to the left, and so on. It's going to come here. Now, in this particular case, this is a slightly interesting case because it says that, well, there is no match between A and B, but because 1 is greater than or equal to 1, okay, there's a greater than or equal to sign. So we're going to put an arrow going upwards. Okay, we're going to prefer going upwards rather than left, although you could have gone left as well. Okay, but this is how the algorithm has been written, that if the two are equal, the top and the left are equal, we're going to choose one of the two, and we're going to choose the one at the top. Okay. Similarly, over here, you can see that when all three of them are equal, all three of them are equal, we're going to choose the diagonal arrow. Okay, why is that? Because we're basically going to start off with the first condition. We're going to say, well, there is a match. And when there is a match, we need to do something a little differently. Okay, we need to increment. And when we're incrementing, we're going to use the diagonal arrow because we're basically saying that when you're incrementing, we are basing the solution based on a smaller version of X and Y. Okay, we're taking the smaller versions of X and Y and we're incrementing that. Okay, so the diagonals have a little different importance in the solution versus the vertical or horizontal arrows. So hopefully you can see that you can work through this, and at the end of it, as we go through this in the row major order, okay, we eventually end up over here, and this is the last point at which we stop the algorithm. The question now is, how do we get first of all, the length, which is hopefully kind of obvious because now 4 is the longest LCS, which is what we have. And a slightly tricky question here is, how do we actually print the length, the actual LCS? Because we're looking for two solutions, the length as well as the actual LCS. Yes, Logan. Yes, so this is in fact a matrix. So C and B are two-dimensional matrices, integer matrices. Yeah. So now the question is, how do we get the actual LCS? And looking at the solution, and there's a lot of hints in there. Some of the character letters are actually circled, so you can obviously see that the LCS is kind of right in front of us, right? But how do we actually derive that? And can you think of an algorithm to actually derive the LCS, the actual longest common subsequence, from this matrix, which comprises of both B and C matrices? And they're sort of superimposed on each other right now. B matrices having the arrows and C matrices having the integers. Yeah. Okay. Yeah, exactly. So did people follow Isaac's solution, right? Basically, what he said was that you start from the bottom right corner of the matrix, okay, for the value of C, M, and N. That's where you start off. And in fact, CMN gives you the longest subsequence. Okay, so this particular value over here is actually the solution to the question, what is the longest LCS? And so that is the solution. And then if you want to print that out, the suggestion from Isaac is that you start off and follow the arrows, which are part of the B matrix. And every time you see a diagonal arrow, that's where you select either the X or the corresponding Y value, which they both happen to be the same. Okay, so you're not selecting the values when you have either a vertical arrow, okay, because in that case, D and B don't match. So obviously it doesn't make sense to pick one of the two. But when you do have a match, that's when you're using the diagonal arrows. Okay, so in this case, B and these two are matching. And when you're following either the vertical arrows or the horizontal arrows, you're simply following that particular path. And once you've gotten to the original, to right to the bottom of the tree, of the matrix, and you hit this particular point, then you sort of backtrace, okay? And you keep track of that through maybe a recursive call, and you've got the solution, and you sort of do a post print. So you get B, these are the diagonal spots. This is B over here, and then you have a C, and then you have another B, and then you have an A. Okay, so so this is sort of a little bit more of an explanation on B, but essentially this is what you have: B, C, B, A. Okay, and this is the solution for the printing algorithm. Basically, what it's saying is that you're doing a recursive call, and you're doing a post print. So initially, if these two are equal and there is a diagonal arrow in B, then you're going to go for the in the direction of the diagonal. So you're going to make X smaller and the value of Y smaller. And you're going to pass it the original X values and the original B matrix. And then once you recurse through all of that, at the end, you're going to do a post print. Okay, so that's going to make sure that prints it out in the right order. Okay, if you have a diagonal arrow, you do a printing. If you have a vertical arrow, or the last one would be a horizontal arrow, you simply do a recursion, and you look at either the one above or the one on the left. Okay, so so that was, I thought, an interesting algorithm, an interesting way of solving this problem. And I guess the next question is, if you remember what the exhaustive solution complexity was, and if you think about the complexity of this algorithm, is there a difference? Is there a huge difference? What would be the complexity of this algorithm? Okay, and if you look back, this is the actual algorithm. This is simply printing it out. And the printing part is perhaps a little simpler, but if you look at the original algorithm, what do you think is the complexity, Logan? Yeah, so it's going to be m times n, simply because you iterating through a double nested loop, and you're going from I is equal to 1 to m and j is equal to 1 to n. So it's exactly m times n. Okay, and there's no more complexity over here. So all of a sudden, you've gone from m times 2 to the power of n to m times n. So that's a huge reduction in complexity. Okay. And that's what dynamic programming does for you. And what about the space complexity? Yes, Kyle. That's how big the matrix is. Yes, I think that's a mistake over here. For print, yes. So for printing, for the original algorithm, both of these are m times n, and for the printing, it's simply m plus n, because you're sort of going in one particular, you're sort of picking a linear path through the two-dimensional matrix. Okay, so the complexity of the print LCS is a little smaller. Okay, so if you followed all of that, that's great. And so you wouldn't mind answering this particular question. What if we replaced the greater than equal to sign over here with simply a greater than sign? How would the result be different, if at all? Yes, Jane? Why wouldn't there be no difference? So sorry, no difference to what? There are two questions we're asking. First is what is that integer number, which is the longest subsequence? And secondly, we're printing it out as well. So are you saying both of them are going to be the same? The integer you're suggesting will be the same. Okay. What about the actual LCS? Will the characters be the same or different? Because remember, there can be multiple LCSs. Might be different. So what would it be? What would the characters be if you picked a strictly greater than inequality rather than greater than equal to? Okay, so the last one will be a B. Okay, so very good. So basically, instead of having, as I said, the default was when these two numbers, the top and the left, are equal, then we pick the top one. Okay, and that's because we had a greater than equal to sign. All right, but if we simply have a strictly greater than sign, then we're saying that we won't follow the second loop. We'll only follow the second loop if this is greater than. Otherwise, if they're equal to, then we'll follow the third, and then we'll use the left arrow. Okay, so if you're doing the left arrow, can you tell me the solution? So the last character would be B, and before that would be A. Okay, because now you're going through the diagonals. And then you're following this particular path. And then did you say? Did you follow this particular path? So you were sort of partly, sometimes you're going upward, sometimes you're going down, leftward, which is also a solution, right? But let's say we consistently using this greater than sign. And so we consistently going to the left. Okay. So what would the solution be then? Would be D. We're following this particular path, and then a B. Okay, so B, D, A, B would also be a solution because we just followed a different path. Okay, and that's perfectly fine. So that's what I've shown you over here. This is what we're doing. We just have the arrows pointing in the different directions. And of course, if you chose to randomly select either to go left or the top, then you could have other solutions as well. So you could go this way, and sometimes you're going left, okay, when these two are equal, okay. At other times, when these two are equal, you're going topwards, okay. So you can come up with a whole bunch of solutions, and there could be a really large number of solutions as well, okay. But in this case, I think there are only 3 solutions. I can only see 3 paths through this, but maybe you can see more. So that brings us to the end, the LCS problem. And since we have 9 minutes left, I'm going to start looking at the next problem. Yes, question. Practical applications for example, matrix multiplication. Oh, okay. The new LCS algorithms have any? So I haven't really looked at, honestly, the new LCS algorithms. And it's quite possible that I'm sure that they've been published, that there is hopefully a reduction in complexity. Okay. Well, let me retract that. It's quite possible that the complexity is still the same, but the constants associated with the complexity have been reduced. And the actual real life solutions, the constants make a big difference. Okay, so if, yes, there's a question back. Is there? No. Okay. So any other questions as far as the LCS solution is concerned? So if not, let's take a look at next algorithm, which is referred to as the matrix chain multiplication problem. Okay, and this is also one of the solutions, one of the subsections in the book, and it has a different technique. The problem is quite different, and each one of these solutions is somewhat different, but in general, they're following a certain similar strategy. Okay, and so once you've seen, hopefully, several of these techniques, you should be able to get a better idea, a better grasp of DP. So the problem is quite an interesting problem, and actually, you might think, well, how often do you have a chain of matrices that need to be multiplied? Okay, so we're basically saying that if you have a chain of matrices, A1 through AN, and they need to be multiplied, all of them together, not just two matrices, but a whole bunch of them, and n could be, let's say, 100 or really large, then we need to find an optimal solution to the sequence in which you can multiply these. Okay. Now, can one think of applications of such a problem? Because it's always interesting to think of where those problems actually originate from. So in the previous example, I said I gave you examples of two applications. The one was genome sciences. The other was, I mentioned that. Does anybody remember what could be the other example where you could be using LCS? Nothing to do with DNA strands. Yes, yeah. NLP, yes. So that's the one that I mentioned, that in NLP, you want to keep the order of the words to be the same, and then to be able to make, to be able to compare to perhaps two sequence of sentences, and to be able to see which can you find one of them to be closer than if you have three strings, which two of them are closer to each other. Okay, so it's an important problem in NLP as well. So what about this? When would you think you'd need to multiply a whole series of matrices together? Can anybody think of an application in real life? Yes. Yeah. So in machine learning, in graph theory, yes. So when you have graphs, then you generally represent them as adjacency matrices. And then when you're manipulating graphs, then you have a lot of matrix multiplications. Okay. And if you're doing, if you like to do game programming, okay, if you'd like to develop games, then generally every image in a game is actually represented by a series. It's a vector. So it's a two-dimensional vector, or maybe three-dimensional, right? And to be able to go from one instance to the next one, you generally have to do multiplications. Okay, so matrix multiplication, you may not realize it, but it's an extremely important problem, and comes in a lot, especially in networks and other areas. Okay, so let's see how we can try to first of all understand what the problem is, and then we can try to see if we can resolve this. So remember matrix multiplication from linear algebra, perhaps? So if you had two matrices, A1 and A2, and A1 is of size P0 times P1, okay? And A2 has to be the same, so these two have to be the same. So the number of columns in A1 have to be this number of rows in A2 to be able to have a multiplication of these two matrices. So P1 here is common, and P2 can be different from P0. So the resulting matrix is of size P0 times P2, right? So this is something that you already know. What is the number of scalar multiplications? So there's going to be a whole bunch of operations when you do this matrix multiplication. That's going to comprise of multiplications as well as additions, right? But additions generally are similar to implement, and multiplications are a little bit more intensive. Okay, so inside your hardware. So generally we look at multiplications to determine what is the cost of this operation. So can somebody tell me, in terms of scalar multiplications, what would be the number of scalar multiplications required to do to calculate the entire A1 times A2 operation? So what do? We take this row over here, and we multiply it by this particular column, and that's how we get each one of these parts. Okay. So what would be the complexity of this operation in terms of P0, P1, and P2? So think about it in terms of the final matrix. This is already P0 times P2, right? Yes, Jack. Yeah. So it's going to be simply P0 times P1 times P2, simply because P0 times P2 is the size of the final matrix, and each one of them, to be able to calculate each element, requires P1 multiplications. Okay, so you need to multiply. There's a whole bunch of additions as well, but you're not excluding the additions. So, so that's the number of scalar multiplications required to do a single matrix multiplication. Now the question is, and now let's define a sequence over here. Then perhaps we're going to stop over here. So let's define a sequence of dimensions. So we can represent the sequence as follows. So if you have, for example, A1 and A2 with n is equal to 2, then you can see that there is a repetition. So we're going to use a shorthand notation, which is simply going to say that we're going to represent the sequence of sizes by P0, P1, and P2. Okay. Similarly, if you have n is equal to 3, the sizes could be represented by a sequence P0, P1, P2, P3. If you have a sequence of matrices going from A1 through AN, because these values are going to be the same, you don't have to repeat those, and you can simply represent the sequence of dimensions by going from P0 all the way up to Pn. There's one additional value, which is P0, but the rest of them are essentially the starting dimension of each one of the subsequent matrices.